Hi everyone, welcome to lecture 22, Physics 2001, section 102. This is the lecture on thermal physics. Just so you know, this traditionally is over 2 courses, so quite a bit of content has been just cut out of thermal physics. In case that you're curious, there are supplemental slides at the end of the PDF that's posted into Long Kappa. Those will not be on the homework. You do not have to know any of that information. I just wanted it to be there in case you were curious. So again, we're talking about thermal physics here. As a general reminder, if you have questions, please email me. I will post the question and the answer, question without your name and the answer, to a Google Doc. If you see the Google Docs empty, that means there were no questions, which is fine. And the course webpage also has the slides and video links, but you know that because you found the video clearly. So we will be talking about thermal physics today, and as usual, it's all summarized right here, most of what you need to know. Okay, so thermal physics, what is it basically? It's trying to understand heat and temperatures. So for instance, you might wonder, why can you only see warm things in infrared and not cold objects? Right? Why do bridges have these expansion joints? Why do you need to have those? Which is also related to why your sidewalk cracks in certain neighborhoods. And you might wonder, how much energy does it really take to bring water up to a boiling temperature? How would you calculate that? So that's the kind of thing that we're going to cover today. Okay, so temperature and heat are two concepts that may be conflated occasionally, and they are different. So let's talk about what those are. So what's the temperature? That's really a measure of the internal kinetic energy of the atoms and molecules within an object. So objects that have any temperature at all, which is everything, that's manifested by energy being stored via rotational and vibrational motion of solid objects. And in liquids and gases, it's really like kinetic motion of the atoms and molecules within that fluid. So this temperature is a measure of that internal kinetic energy. This is just a property of an object, right? So it's a collective property. And for instance, like when you heat something up in a microwave, you're basically exciting rotational motion of water molecules, and that is what is heating up the food. Is you're basically causing those water molecules to rotate a bunch, and that is how the heat is stored. So that's temperature. What's heat? Heat's a measure of the transfer of the energy between two objects. So the temperature measures the kinetic energy of an object, the internal kinetic energy, and the heat measures the transfer between two objects. So it's always kind of a relative thing. So it's a property of an interaction. It's not a property of a single object. So heat, right, that's moving energy from a high temperature to a low temperature object. That's all that heat is. And so heat transfer is always going to be energy transferring from a warmer object to a cooler object. That is always what is happening. And so for instance, if you touch a stovetop, that hurts because there's a lot of energy being transferred from the hot stovetop to your colder hand. If you touch, let's say, an ice cube or some really cold object, that hurts because a lot of energy is being transferred from your hand to the colder object. So the heat's always transferred from the hot thing to the cold thing. And in the case of why you can get burns from heat or from cool, it's the basic concept is you just have a big energy flux through your skin and it hurts. But it's always heat going from hot to cold. So there are, several different temperature scales that are commonly used. So there's a few common units that we wind up dealing with. So the three main ones are the Fahrenheit, Celsius, and Kelvin. So Fahrenheit, that's the one that most of us use in the US that we're used to. And so you guys are very familiar with that scale, I'm sure. So you may be less familiar with Celsius. So how do you relate it to Celsius? The temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. Okay, so that's just the conversion. Historically, Fahrenheit is just kind of an older temperature scale that people just never gave up. Celsius is one that was sort of more, I would say, intelligently designed. was intelligently designed with some forethought. So the Celsius scale, right, 0 is defined as water freezing, 100 is defined as water boiling, and so that's where that comes from. Fahrenheit, just has a different historical basis, and so you get 32 is freezing and 212 is boiling. Okay, so this temperature in Fahrenheit is related to temperature in Celsius by this way. Now, if you want to see what the change in temperature in Fahrenheit, how that's related to the change in temperature in Celsius, this constant would cancel. So the change in temperature in Fahrenheit is equal to 9/5 the change in temperature in Celsius. The 32 is just an offset. So Celsius, you can relate that to Kelvin. Kelvin is the absolute temperature scale. This is an even more scientific one that was after people thought about it harder. How should we define temperature? The Kelvin scale was invented, and the idea with Kelvin is that there is an absolute 0. So the lowest possible temperature in Kelvin is 0. So there's no negative temperatures in Kelvin. And the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. So 0 Kelvin is absolute 0. That's the lowest possible temperature. You cannot go lower than that. It's just a definition. 0 Celsius, right? That's the freezing point for water. That's 32 Fahrenheit, which is 273.15 Kelvin. 100 degrees Celsius, that's the boiling point for water, which is 212 degrees Fahrenheit, which is 373.14 Kelvin. Now, to help you check with the reasonableness of your answer, there's this basic thing you can keep in mind. 20 degrees C, that's about room temperature. 0 is freezing, 10's pretty cold, 20's comfortable and nice, right? 30's hot. So that's a basic way to remember it. 10 is cold, 20's nice, 30's hot. So that's just defining the basics of heat and temperature. Now let's look into a practical consequence of adding heat to an object. So that's thermal expansion. So we're only going to consider linear expansion. If you want to consider areal or volumetric expansion, that is in the supplemental slides. But again, you do not need to know anything in the supplemental slide. It's just there for your own curiosity. So when an object's temperature increases, it expands. Okay. And the amount of expansion is going to depend on the material properties, and it is known as the expansion coefficient, alpha. That's the variable that we use, so it's a lowercase alpha. Alpha depends on the particular material and on the phase of the matter. So the SI unit is the inverse Kelvin. So the coefficient has units of 1 over Kelvin. And what alpha does is it describes how much an object expands in a linear dimension for a given temperature increase. So there's the picture here in the upper right where you have some rod that has some length at a nominal temperature that we're going to call T naught. You increase the temperature by some delta T, and you see the length increases by some additional length, some delta L. And alpha tells you about that expansion. So delta L, this extra bit of length that this rod now has, this is equal to alpha times the original length of the rod, or whatever object we're talking about, times the change in temperature. And because alpha is in units of inverse Kelvin, then here we're talking about the change in temperature in Kelvin, right? Now, you can get away with using the change in temperature in Celsius because there's only a constant offset between Kelvin and Celsius, so that's fine. You cannot just use Fahrenheit, right? The change in temperature in Fahrenheit, unless you convert the units of alpha. Because remember, the change in temperature in Fahrenheit is 9/5 the change in temperature in Celsius. So what's the fractional change in length? By how much does a object expand? That would be delta L over L. So you're dividing the extra length by the original length, so delta L over L naught in the picture, and that is equal to alpha T, so the coefficient of linear expansion times the change in the temperature. So remember, as I said, that this temperature delta T needs to be in Celsius or Kelvin because of the way that the because of the SI units for the coefficient. So these are all things that you need to know. And here I highlight this is in a linear dimension because it's going to be different for a volumetric expansion, which again, you do not need to know for this semester. So this is why you need joints, expansion joints in things like bridges. So a bridge that's sitting out in the air is going to change temperature quite drastically and quite rapidly. It's not touching the earth as like a nice thermal heat bath. And so that bridge is going to expand and contract as the temperature does. And so what you can do is just take advantage of that by having these expansion joints. You leave a little bit of play, a little bit of room for it to expand and contract as the environment temperature changes. So you might wonder, what are some typical alpha values? So here are just some typical examples. So when you start out with a material at 20 degrees in Celsius, you see that it's on the order of 10 to the minus 5 inverse Kelvin. So some metals are like 2 times 10 to the minus 5. Some other materials here, some composite materials, it's more like 1 times 10 to the minus 5. Diamond, a very hard material, one that is, it can deal with a lot of stress and strain, that's smaller. That's 0.1 times 10 to the minus 5. So this is going to be a smaller length for a given change in temperature. Let's do an example. So let's say we have a half-meter long rod and the thermal expansion coefficient is 10 to the minus 5 inverse Kelvin. We're going to heat it from room temperature, which room temperature is about 293 Kelvin, so it's about 20 C, right? To boiling temperature of water, which is around 373 Kelvin. The question is, how much extra length does the rod have after you heat it? So I'm going to assume that you've paused and used that equation. Let's see. So it's 4 times 10 to the minus 4 meters. So we use our equation that the change in length is equal to alpha, the coefficient of linear expansion, times the initial length of the rod, times delta T. And you can plug in the numbers that we have, and you see that it is 4 times 10 to the minus 4 meters, which is 400 microns, which for some context is 4 human hair widths. So this is why you may not have really noticed this linear expansion much in the past, is that you need a relatively large change in temperature if you want to see this change in length for a small object. For a bridge, it's a bigger deal because a bridge is a very long object, and so you still have a small delta L over L, right? The fractional change in length is still small, but the absolute change in length is significant. So you need to include these expansion joints to take into account that little bit of extra play, right? So if you had the same change in temperature and the same coefficient, linear coefficient of expansion, if instead, let's say you had a 500 meter long rod, that's 1,000 times larger, well, that's a 0.4 meter or 40 centimeter change in length. So that is now appreciable, right? So now let's do another question, but this is kind of an interesting consequence of our coefficient of linear expansion for different materials. So let's say we have a bimetallic strip. So these are defined as you basically have one metal sandwiched together with another type of metal. So they're two different types of metal that are glued together, for instance, or welded together. So one metal's on top and the other type of metal is on the bottom. If the metal on top has a smaller thermal expansion coefficient than the metal on the bottom, which picture best represents what is going to happen after your bimetallic strip is heated? I'm going to assume that you have paused and you have come back, and you'll see that 1 is what's going to happen. So again, the linear expansion is your alpha, your linear expansion coefficient, times the original length times delta T. Both of these strips have the same initial length. We're looking at our delta L over L here. And you're presumably going to experience the same delta T for each of them. So the question is really what's going to happen with alpha. So the top strip has a smaller alpha and it's going to expand less than the bottom strip. So if we want to achieve the extra length on the bottom without lengthening the top half by the same amount, then the strip is going to be forced to bend upwards. That's just what's going to happen, basically. And so this, for instance, this is how some older spring-based thermostats work. So you can, for instance, bust open a thermostat in like a lot of the older academic buildings or an older house, and when you look at it, you'll see this kind of coiled metal. And that coiled metal is often a bimetallic strip. And so as the temperature changes, this thing will curl up a bit more or open up, depending on whether you're heating or cooling. And that basically is going to then that you can basically move a dial in that way by this thing coiling up more or less. You can have, for instance, a dial attached to the center, and that will, or on the end, either way, and that will basically then convert between the change in temperature and a dial reading, which is kind of amazing. Okay, so let's talk a little bit more about heat. So heat, right, this is the thermal energy that flows from a high temperature object to a low temperature object. That is the definition. It depends on the parameters of your process. These are called state variables. So the internal energy of the objects, that is a state variable, which essentially tells you the kinetic energy of the atoms and the molecules inside. We are going to use the variable U to discuss the internal energy. And there is the temperature of the objects, T. So your body radiates heat to the surrounding environment as light. So we see that light in infrared wavelengths. So, right, light carries quanta of energy, and if you're warmer than the surrounding environment, then you're going to transfer heat to that cooler environment around you, and the most effective way to transfer that heat is radiative cooling. That's one of the effective ways, and so basically your body gives off light. Which of these processes is going to require the most thermal energy? So we want to raise 1 kilogram of water by 10 Kelvin, 2 kilograms of water by 10 Kelvin, 2 kilograms of water by 20 Kelvin, or are they all going to take the same amount of thermal energy? So I'll assume that you've paused and you've come back and see. It takes 22 kilograms of water, 20 Kelvin. That is going to require the most thermal energy, right? The reason is that more heat is going to be required to create a larger temperature change, and the more material you heat up, the more energy it's going to take. So here, for part B, I'm raising the temperature of more material by the same amount compared to part A. That requires more heat. But then in part C, I have more material than in part A, and more of a temperature change than in part B. So that's going to require the most energy, just in a qualitative sense. Then we're going to solve or talk about this quantitatively in just a moment. So right, heat, that's the energy required to change an object's temperature. More heat is required to raise the temperature of a larger object. That makes sense. More heat is required to induce a larger temperature change. That, of course, also makes sense. So the exact amount of heat is going to depend on the properties of the material. These are described by the specific heat capacity, so that's lowercase c. C is the amount of energy required to raise the temperature of a given mass of a particular material by a certain temperature change. Okay, so the SI unit is joule per kilogram per Kelvin. So for instance, if you have C is 1 in SI units, then that means it takes 1 joule to raise 1 kilogram of that material 1 degree in Kelvin. The typical values for the specific heat capacity are 100 joules per kilogram per Kelvin. One thing that I don't know if most of you are going to deal with, but there is a difference between heat capacity and specific heat capacity. Specific heat capacity means we're dividing by the mass, and so that's why it's joules per kilogram per Kelvin. The heat capacity itself doesn't have the kilogram in the denominator, but we're going to work with specific heat capacity So that's going to be joules per kilogram per Kelvin, and 100 is a typical value for a lot of materials that we deal with. So it turns out aluminum has a 10 times higher specific heat capacity than this. That's atypically large for a solid. Okay, so what does that mean? It means it takes a lot of energy to heat that aluminum up. Okay, so that's, for instance, why you might use aluminum foil to wrap a baked potato, as your aluminum is not going to heat up nearly as much as your friend, the baked potato, because the aluminum has a much higher specific heat capacity. It turns out liquid water has an even higher specific heat capacity. But it's a liquid, not a solid, right? So aluminum is very high, quite high for a solid. So let's formulaically, the formula that we need to know is this formula Q, the heat transfer, is equal to the specific heat capacity times the mass of an object times delta T. So Q is Cm delta T. All right, so if the temperature of an object decreases, it will release heat into the environment. So if an object has some extra heat and it cools, it's releasing heat into the environment. If instead you have, if you want to raise the temperature of an object, right, that requires some heat input. So the situation on the left here, we're adding heat that raises the internal energy that raises the temperature. If we have a really hot object surrounded by a cool environment, then this object is going to transfer heat to the environment and its temperature is going to lower of the object. Now, an important thing is this equation here does not describe the phase change. So transitioning, for instance, from liquid water to solid ice, or from liquid water to water vapor. We're going to cover that in a minute. So this is formula, this Q is Cm delta T. This is what you use when you're in between phase changes. So let's say you want to heat up a 1 kilogram block of aluminum and a ½ kilogram of water by 20 Kelvin. Which of these processes is going to require the most thermal energy? And for your information, something you're going to need to know is the specific heat capacity of aluminum is about 900 joules per kilogram per Kelvin. Water is about 4,000 joules per kilogram per Kelvin. So I'm going to assume that you have worked on this and come back, and you'll see that the water is the one that requires the most thermal energy. So again, Q is mc delta T. The heat transfer is equal to the mass times specific heat capacity times change in temperature. So we can go ahead and plug in the information for the aluminum. And you have 1 kilogram, 900 joule per kilogram per Kelvin, 20 Kelvin, and you get 18,000 joules of energy required to do this. The water, on the other hand, you plug in its mass is less, but its specific heat capacity is much larger, and that winds up turning into 40,000 joules required to heat this. So therefore, your water is going to require more heat. So this heat transfer concept, this can be really useful in terms of calorimetry. So you can basically measure temperature changes, and that tells you how much heat was released from something. So for instance, let's say you have a chemical reaction, and you want to know how much energy is produced by that chemical reaction. You can do that chemical reaction inside of a fluid and measure the change in temperature in the fluid, and that tells you how much heat was released in the reaction. So if you've ever wondered, how do we know, how much energy is released by burning a given fuel? Well, calorimetry is the way that you do that. So you take advantage of this Q is mc delta T, or Cm delta T. So you measure the temperature before and after the reaction, that gives you delta T. So you can measure the mass of the fluid that you're going to be heating, and you need to know the specific heat of that fluid. And then you can determine that the heat energy is Q is mc delta T. So the energy lost by the chemical reaction, right, is gained by the surrounding environment. So the idea is that Q lost is Q gained, right? So the heat, the energy is conserved, and so the energy emitted by the hotter object is then gained by the cooler object. And it does not mean that you're going to wind up at the mean temperature, because the specific heat capacities are different, as we will see. So this is the idea for calorimetry, is you have some hot object, and it is going to release heat, and that heat is then going to be gained by the cooler object. So the temperature of the hot one goes down, cool one goes up. And a simple example is this like styrofoam cup calorimeter that you could use if you wanted to. So a key detail here is that the stuff that you care about, the system, so in this case the system is your chemical reaction, chemicals that are undergoing that reaction, and the water in the picture, they need to be thermally isolated from the surrounding environment. So in this case, in this example, you would use styrofoam cups to do that thermal isolation. So for instance, you could put one cup inside another. That's going to create a pretty good thermos, and that will mostly isolate this system here. So let's say we have 2 liters of water at 353 Kelvin. We're going to add that to 1.5 liters of water at 293 Kelvin. No energy is lost to your surrounding environment. The question is, what is the final equilibrium temperature of the water? And what you need to know is that 1 liter of water has a mass of 1 kilogram, and the specific heat of water is about 4,000 joules per kilogram per Kelvin. So I'm going to assume that you have worked on this and come back, and you'll see that the final equilibrium temperature of this combined water is 327 Kelvin. So the energy lost by the hotter water is gained by the cooler water. So on each side, the heat is still mc delta T. So we have the mass of the 2 liter of water times the specific heat of the 2 liter of water times its change in temperature is equal to the mass of the 1.5 liters of water times its specific heat capacity times its change in temperature. And of course here, the specific heat capacity is the same for these two objects because they are both water, so that's going to cancel. So then we can just plug in the mass of the 2 liter of water. Its change in temperature is going to be 353 Kelvin minus whatever the final equilibrium temperature is. The cooler water has a mass of 1.5 kilograms. Its change in temperature is going to be the final minus its initial, and you can solve this equation. And I just want to point out, why are we subtracting the final temperature on the left, but subtracting the initial temperature on the right? And that's because we know that the hot thing is going to get cooler, and the cool thing is going to get hotter. And these equations only make sense if you have a positive heat, right? Because we're saying heat gained, that's a positive number. Heat lost, that's a positive number for the hot thing. So that's why you do this. You subtract the final for the hotter thing, you subtract the initial for the initially cooler thing. So then here I'm doing what you should never do, and I'm plugging in the numbers before I do the algebra. But ultimately we do the algebra, and we find that the final temperature is 327 Kelvin. Okay, so now let's do a problem where we have to consider mixing objects of different specific heat capacities. So let's say you start out with 2 beakers of water that have identical initial conditions. So each beaker contains 1 kilogram of water at 293 Kelvin, and the specific heat capacity of the water is listed there. Now in beaker 1, you're going to drop a 353 Kelvin block of 1 kilogram of aluminum. In beaker number 2, you're going to take a 353 Kelvin 1 kilogram block of copper, and you're dropping it into beaker 2. And I want to note that aluminum has a much higher specific heat capacity than the copper. Okay, so the question is, once the beaker reaches thermal equilibrium with the block, which beaker is going to have the higher temperature? So take a moment, pause, think about it, and work on it. I'm going to assume that you have paused and you have come back, and you'll see that the beaker with aluminum is going to have a much higher equilibrium temperature. So the aluminum, right, has a much larger specific heat capacity than copper. So that means it takes more energy to change the temperature of aluminum. And so it also means that more energy is deposited by a change in temperature of the aluminum block relative to the copper. So that's just the qualitative answer. You don't need to do any calculations in order to solve that. If you wanted to do this mathematically, so let's say, for instance, we started out with slightly different initial temperatures for our blocks, or they had slightly different initial masses, or we were using slightly different fluids. How would you figure out this mathematically? And so that's what's shown here. So remember, the energy lost by the hot object is equal to the energy gained by the cool object. So we're going to do this mc delta T for the block is equal to mc delta T for the water. And we can then work through the algebra, and you can figure out what the final temperature is going to be. And you know, it looks like a sort of intimidating equation, but it's not too bad. All you did is you started out with your mc delta T for block is mc delta T for the water, and the final temperature of each of these objects is going to be the same when you reach equilibrium. For the hot object, you do the initial temperature of the hot object minus the final equilibrium temperature. For the cold object, you do the final equilibrium temperature minus the initial temperature of the cold object, and you just crank through the algebra and you get this answer here. And so then you could solve quantitatively for what the equilibrium temperature is going to be. Okay, so another consequence of heat transfer is that you can do thermal energy storage, right? So you can use large objects as energy reservoirs by storing energy as heat. So the excess energy can be stored as heat to be released later, or you can use it to smooth out the power distribution from a different energy source. So let's say you have an energy source that produces intermittent power, then you might want to store that in one of these tanks so that you can smoothly distribute that. So for instance, solar energy can often be quite intermittent because clouds come in and they block the sunlight, and you don't collect as much energy from the solar panel. So it's often a good idea to couple solar power with some kind of thermal energy reservoir. So for instance, right, even if you don't have a lot of cloudy weather, you can store solar energy from day to night. Wind energy can be stored this way. And if you think about it, the Earth itself, that's a large hot object. So the heat is mostly coming from radioactive decays inside the Earth's core. You also have heat from sunlight. And this heat forms the basis of geothermal energy. So the Earth, the radioactive decay is producing heat. That is then being stored as thermal energy in the Earth. And you can run some water pipes through the ground, and you can basically send room temperature water in through the ground, and that will be heated up, and there you go. So you might say, well, this doesn't sound that effective. I mean, you'd need something huge to do this, and you do indeed. And so often these are done under sports stadiums and parking lots. So I know that some of the sports fields on the campus of Michigan State University, when they redid those a few years back, those are now geothermal energy producing sources. So let's do another practice problem with heat transfer. So we have a 1 kilogram block of aluminum. It has an initial temperature of 300 Kelvin. The block is placed over an electric heater, and the heater provides 150 watts of power for 300 seconds. And remember that watt is a joule per second. So after this heating episode, the question is, what is the temperature of our aluminum block? So I'm going to assume that you've paused, worked it out, used Q's mc delta T, and come back. So it's 350 Kelvin. So again, we have the heat transfer. This is the mass of our aluminum block times the specific heat capacity of the aluminum block times its change in temperature. So we can solve for the change in temperature based on the heat transfer. The heat transfer, right, this is just going to be our energy times time. So there was 150 watts of power times 300 seconds. So we know 450,000 joules of energy are being transferred via heat. And then we can plug those numbers in, and we get that the change in temperature is 50 Kelvin, And this is where you have to be careful. A common pitfall is to solve for this and be happy. You solve for the change in temperature, but we want to know what the final temperature of the aluminum block is. So you have to add this delta T to the initial temperature, and you get that is 350 Kelvin. Okay, so far we've talked about when a material is in one single phase. It's always a solid, or it's always a liquid, or it's always a gas. And if you want to change the temperature, you use that Q is mc delta T, that heat transfer equation. Now, what about changing phases? What if you want to go from a solid to a liquid to a gas? How do you do that? That clearly costs or releases some energy, so we need to take that into account as well. So, right, the phase change is just defining going from, for instance, solid to liquid to gas. If you want to go from a solid to a liquid to a gas, you are absorbing energy. So you absorb energy in your solid to go to a liquid to go to a gas. If you want to go the other direction, energy is released. Okay, and a way to remember this is ice is a solid. If you want to turn it into a liquid, you got to heat it. If you want to turn it into a gas, you got to heat it more. So you're absorbing energy, whereas in the other direction, energy is going to be released. So the latent heat, this describes the amount of energy that needs to be absorbed to change phases, or the amount of energy that is released upon a phase transition due to breaking or forming molecular bonds. So if you are heating, if you're going solid to liquid to gas, that the latent heat is the amount of energy you need to absorb. If you're going the opposite direction, gas to liquid to solid, the latent heat describes how much energy is released in the phase transition. Okay, so energy needs to be absorbed for the solid to liquid to gas, or solid to liquid or liquid to gas. That's an endothermic reaction. Energy is released for the opposite direction, gas to liquid or liquid to solid. That is an exothermic reaction. So we refer to going between solid and liquid, whichever direction you're going. That is referred to as the latent heat of fusion. If you're going from liquid to gas or gas to liquid, that is the latent heat of vaporization. Because the amount of energy that it costs to go from one phase to another doesn't have to be the same. So to go from solid to liquid doesn't have to cost the same amount of energy as liquid to gas, and often it's very different. But the energy you must absorb to go from solid to liquid, that is equal to the energy you release when you go from liquid to solid. So the same latent heat describes a given phase transition from one to the other, solid to liquid or liquid to solid, but it's very different whether you're talking about fusion or vaporization. So the latent heat that is either added or removed during a phase transition is that heat Q is mL. So the mass of the object that we're talking about times the latent heat of either fusion or vaporization, L. So that's the formula, Q is mL. So what you always need to pay attention to is, am I absorbing energy or am I releasing energy? And am I going between solid and liquid or liquid and gas? And that tells you whether you're talking about fusion or vaporization. So if we take a look at how much heat is required per unit mass to raise an object by a given temperature, here we're looking at water, you get the following curve. So in the linear portion, the part that has some slope, this is our Q is mc delta T. This is the formula we were talking about previously. Then in your phase change, this is the heat you're paying to do the phase change. So to go from ice to water, you need to add in heat, and you're paying, what you're absorbing in this case is the mass of the water times the latent heat of fusion. Then you can continue to heat the water to raise its temperature. This is Q is mc delta T. And then finally you reach the boiling point of water, and now more energy has to be absorbed in order, so we're absorbing energy that's moving horizontally, absorbing energy, and then finally you have absorbed enough energy, you have absorbed this mL, mass of the water, times latent heat of vaporization, and you've paid the energy to convert to steam. And some example for water, here are the different latent heats. So you see for vaporization, this is about 10 times more energy than fusion. And then you have different specific heat capacities. For ice and steam, quite similar. For water, it's about twice as large. So, as I said verbally here, if we want to think about the amount of heat, let's say we're starting out at minus 20 C with our ice, and we want to make it up to some temperature of steam. The heat that we have to pay, we can break it into these 5 different amounts of heat, A, B, C, D, E. And in A, we are using MC delta T. We finally reach the temperature for the phase transition to go from solid to liquid, that is 0 C for water. And now we need to pay or absorb heat B. So that's the mass of the water times latent heat of fusion. Once that energy has been paid, then the water can begin to heat up. It will begin to change temperature, and you can continue to absorb energy, this MC delta T, until finally the temperature has reached 100 C, the phase transition energy to go from liquid to gas for water. And now you need to pay or absorb this extra heat, which is the mass of the water times the latent heat of vaporization. And once that energy is absorbed, then finally you have gaseous steam, and you can increase the temperature of that steam. So you have to break it down into these components: heating one phase, energy for the phase transition; heating another phase, energy for the phase transition, and so on. So first question is, how much energy is required to melt half a kilogram of ice? So we want to take solid water and turn it into liquid water. So I'm going to assume that you've paused and you have come back. And that is 16.7 times 10 to the 4 joules. So this is a phase transition. So we want to, if we just tell you how much is required to melt it, we're assuming that we're at the proper energy. So the phase transition energy is mass times latent heat of fusion in this case, because we're going solid to liquid. Latent heat of fusion we just gave on the previous slide, that's 33.5 times 10 to the 4 joule per kilogram. And we plug in those numbers, and we get 16.7 times 10 to the 4. And again, if you wanted to actually measure this heat transfer from phase changes, you could again go ahead and use a calorimeter. So let's do a qualitative question here. So let's consider 1 kilogram of material A, which is blue on this object temperature versus heat diagram. So we have 1 kilogram of material A, and we have 1 kilogram of material B. The question here is, which one is going to require the most energy to change from the liquid to the gas phase? So keep in mind, horizontal lines, that's always where you're paying energy, but you're not changing temperature. So that means you're paying energy to change phases. And you basically only have 2 phase changes, right? You have solid to liquid and liquid to gas. So which one of these 2 requires the most energy to change from the liquid to the gas phase? I'm going to assume that you have paused and you have come back, and you'll see that it's B. So why is that? It's because, again, you always, in these curves, you start out as a solid. Your first horizontal line is paying the latent heat of fusion. You're absorbing that to change from solid to liquid. The second horizontal line, this is absorbing energy to go from liquid to gas. And if your horizontal line is longer, then that's more heat. And so B has a longer horizontal stretch than A, and therefore requires more energy to do that phase transition. Okay, so let's do some quantitative problems. So we have a 500-gram aluminum cylinder at 20 C, so that's grams, not kilograms, and it's heated using steam at 140 C. What is the minimum mass of steam required to raise the temperature of the aluminum cylinder by 40 C? And the relevant latent heats and specific heat capacities are listed below. So I'm going to assume that you've paused and you've worked this one out, and now you are back with us. So it's 7 milligrams of steam. which is kind of a lot because it's a gas. So remember, the energy gained by the cold object, initially colder object, is equal to the energy lost by the initially hotter object. So that is always true. It's just energy conservation. So the heat gained by the aluminum is going to equal the heat lost by the steam. And remember, the steam is going to go through these phase changes. It's going to cool. It's going to reach the 100 C transition temperature. It's going to condense to water. There's phase transition energy there. The water is then going to cool. So we have our equation, right? The aluminum is not changing phases ever. It's just a solid the whole time through. So its energy gained is just MC delta T, where you're talking about mass of aluminum, specific heat capacity of aluminum, and change in temperature of the aluminum. The steam, on the other hand, you have the energy lost by the steam when it's just cooling, plus the energy that is released by going from the steam to the water, and then the water itself will cool. So important thing to note here is that it's tempting, since on this side you're always dealing with water, that you have steam and then you have liquid water. And the specific heat capacity for liquid water is not the same as the specific heat capacity for steam. So the mass is going to be the same, but these C's are not the same. So then we can just work through the algebra here. We're trying to solve for the mass of the steam. And we go ahead and do that. Finally plug in all of the numbers. It's kind of a lot, so you got to be careful that you don't make a calculator mistake. And you find that it's about 7 milligrams of steam. So now we have a slug of copper. It's 0.2 kilograms. It's at 800 C. It's pretty hot. Immersed in 0.4 kilograms of water. That's already at 80 C. The final temperature is 100 C. So part of the water is going to be boiled off as steam. So your water basically is heated to 100 C, and that means you're going to be able to boil off some water as steam. So the question is, what is the mass of water that you convert to steam? So again, I'm going to assume that you have paused and you have come back. And you see that in this case, it's 9 milligrams of water. So again, these problems all start out the same. The energy lost by the hot object is equal to the energy gained by the cool object. So the heat lost by the copper is going to warm up the water, and it's going to convert some of that water to steam. And we're told here that the water itself stays at that 100 C, so you don't have an extra term for heating up the water. Okay, you could figure out if that was going to be needed or not. In this case, we just tell you to make life a little bit easier. So we have our copper solid the whole way through, so we're just using MC delta T, whereas the water changes temperature, and then you also have the mass of the steam times the latent heat of vaporization. So we are solving for the mass of the steam once again. In this case, how much we've created. And you plug in all the numbers, and you see that the mass of the steam is 9 milligrams. So that's about 9 milliliters of water. Not about, it is 9 milliliters of liquid water. Let's do one final question here for this lecture. So let's say that it takes 10 minutes for your stove burner to bring 2 quarts of water, which is about 1.9 kilograms, to boiling. So you bring it to 100 C. And it starts out at room temperature, and we'll say that's 20 C. The question is, what is the minimum power output of your stove burner? So let's assume that you have 100% efficiency of heat transfer between your burner and your water. And the power tells you the energy released per time. You can solve how much energy this takes, and you're told how much time it takes. So then you should be able to figure out the power output of the stove burner. And the relevant information is listed in the lower right-hand side of the slide. So take a moment, think about it. I'm assuming you've worked it out. and then you've come back to the video, and you'll see that it's 1060 watts must be the power output of your stove burner. So the power is equal to the energy over the time. The energy, right, is heat. That's all heat is heat's an energy transfer. And here we're just taking it up to 100 C from room temperature. We're not messing with any phase changes in this case. So we're just using MC delta T. We plug in the information about the water, and we see that that is 636,000 joules, roughly. The time is 10 minutes, which is known to its friends as 600 seconds. And so then we can calculate what the power is, the change in energy over time. So this is an equation you guys all remember. You're not allowed to forget anything from the class. The power is energy over time. And so when you divide that heat transfer by the time, you get 1060 watts. So in this case, just in case you care, this is a sixth of a kilowatt hour, right? Because you have 1000 watts is a kilowatt. We're talking about 10 minutes, so it's a sixth of a kilowatt hour. And your typical consumption in the US for a house is going to be 1.3. So it's actually not a negligible amount of the amount of energy you normally would be consuming. It's kind of interesting. Okay, so that is it for thermal physics describing temperature and heat. We will use some of this heat concepts in the following lectures for thermodynamics, and you will see that in a bit. One thing I want to note again is that there are supplemental slides here. As noted, they will not be on any homeworks or exams. They're just in the PDF posted on LonCappa and on the course webpage in case you are curious, because that material had to be cut out due to the pandemic. Okay, so that's it for this lecture.